Okay, hello, welcome back. I didn't realize my video was ending at that moment, so my last little statement got kind of cut off there. So just to summarize what I was saying last regarding the volume receptors, and the role of antidiuretic hormone is the fact that it makes sense if we're in the heat or if we're exercising, it could be a reason, because we're dehydrated. Maybe that's why we don't need to urinate as much. But if we're in the heat also, our brain is actually going to release more antidiuretic hormone, which is actually going to help us retain fluid. So that's a protective mechanism. So that's why we don't urinate as much. We're going to talk about respiration and the cardiac cycle and how respiration influences cardiac cycle. Okay, so inspiration, so taking air in, causes an increase in heart rate. Inspiration is sympathetically mediated. Expiration causes a decrease in heart rate. Expiration is actually parasympathetically mediated. So whenever we inspire, we activate the phrenic nerve. This will cause the diaphragm to pull down and create negative pressure within the thoracic cavity. The phrenic nerve is considered to be sympathetic. When we expire, we turn off the phrenic nerve. This allows acetylcholine to become now the dominant neurotransmitter, which allows heart rate to slow down. Right? So the phrenic nerve is sympathetic. This uses norepinephrine as a neurotransmitter, and it causes an increase in cycle rate. Remember, we are attaching to those beta-1 receptors when we're talking sympathetically. Now let's switch to expiration. We turn off the phrenic nerve, so we're turning off norepinephrine's influence. We increase vagal activity, which then increases the release of acetylcholine onto those cholinergic receptors of the heart, and we will then now have a decrease in cycle rate. Right, so respiration and again cycle rate, let's continue with that. It means that there's a rhythmical oscillation according to our respiratory rate. That's just what we went over. So those neurotransmitters have to metabolize very fast so that the opposing neurotransmitter can then take over and be dominant. So norepinephrine needs to be eliminated, needs to get out of the way so that acetylcholine can take over to expire. So when we inspire, turning on the phrenic nerve, sympathetic neurotransmitters, the dominant as a neurotransmitter is norepinephrine. That's going to act upon the heart, right, onto our beta-1 adrenergic receptors. That's going to increase cycle rate. Now, very quickly, we need to turn that off, right? So when we expire, we turn off the phrenic nerve. The vagus nerve now can then exhibit its effects, release acetylcholine to the cholinergic receptors, and that can become the dominant neurotransmitter of the heart rate, so then cycle rate can slow back down. Okay, so let's sum up breathing and myocardial reflexes in a couple summary statements here. I know this slide is pretty wordy, but I wanted to make sure you had all the correct information as we go over it. Okay, so during inspiration, intrathoracic pressure decreases. As it decreases, venous return is enhanced, so therefore it increases, which is again the amount of blood flow back to the heart. As we enhance venous return to the right side of the heart, we will elicit a Bainbridge reflex, which again is our volume reflex, which is causing an increase in heart rate. So inspiration causes an increase in heart rate, drop in thoracic pressure, enhanced venous return, and causes stretch on those receptors that we talked about on the posterior wall of the right heart, which induces an increase in cycle rate. The left side of the heart will then eject a larger stroke volume. This larger stroke volume will be pushed into the system and trigger the baroreceptors. When triggered, there will be a decrease in cycle rate. This happens when we expire. So this is all related to volume changes and pressure oscillations as the volumes move through the heart and into our aorta and our vessels. Right, so when we inspire, that means we induce a Bainbridge reflex, and then when we expire, it's that baroreceptor reflex we talked about, which was that Mary's law of the heart. Okay, so now we're going to talk about intrinsic control of myocardial function. So what this is referring to is the fact that the myocardium has the capability of regulating its own function without neural and hormonal influences. So similar to what we were just talking about, to the heart having its own intrinsic heart rate at 100 cycles per minute, we're going to talk about other mechanisms too where it can regulate itself. Again, this is without neural or hormonal influences. This just is the heart regulating itself. It has its own intrinsic control mechanisms. We have two types of regulation. Heterometric autoregulation. This is regarding to adaptive changes involving fiber length. 2, homeometric autoregulation is adaptations that do not have to do with fiber length. So 1, heterometric autoregulation has to do with adaptive changes involving fiber length. Homeometric autoregulation, adaptations that do not have to do with fiber length. Okay, so let's talk about the first one, heterometric autoregulation. This has to do with fiber length, okay? So this is what we've talked about before already. This involves a change in preload and on the power of contraction. So this is again back to our length tension relationship. Application of our Frank-Starling mechanism, right? More blood in equals more blood out. That's the key point to the Frank-Starling mechanism here, right? Our fibers have an upper operational limit of 2.2 to 2.6 micrometers. So fibers are becoming more resistant to stretch as we get to closer to that 2.6 micrometers, right? So more volume in, we're putting more stretch on the fibers. We're getting closer to that 2.6 micrometers, and then we're becoming more resistant to stretch, right? Because we can't disengage those cross bridges. This mechanism is the one that allows the ventricle to eject the volume of blood that's returned to it. So anytime we have an increase in venous return, this gives us an increase in fiber length, which is heterometric, which gives us an increase in contractile force, right? Just because the same basic skeletal muscle, cardiac muscle mechanics apply, if we put a little stretch on those fibers, we're going to have an enhanced force. So when we have enhanced force with our cardiac muscle cells or cardiac fibers, how is that going to help us? We're going to eject blood more forcefully and therefore eject a larger stroke volume because of that increase in force. Okay, so when you see the term or hear the term inotropy, this refers to contractility. So any type of inotropic agent enhances contractility. A negative inotropic agent decreases contractility. So examples of a positive inotropic agent is inspiration, our Frank-Starling mechanism, an increase in calcium content, and norepinephrine. So if we have an increase in calcium, that's considered an inotropic agent, for example. Okay. All right, so let's move to that second intrinsic mechanism. We have homeometric induced regulation. Now these are regulations and intrinsic mechanisms that don't have to do with fiber length. Okay, we have 3 of them. 1, something called afterload induced autoregulation. 2, rate induced autoregulation, and then the third one is post extrasystolic potentiation. And we're going to go over all 3. Okay, so afterload induced autoregulation is pretty much what the title says. When we're talking about afterload, right? So when there is an increase in arterial pressure, it is compensated for by an increase in left ventricular diastolic pressure. So as there's an increase in left diastolic pressure, this gives you what you need to maintain that pressure head so we can still eject blood and maintain unidirectional flow. This is what you need to maintain that driving force. So this is important too. Okay, the second one, which we're going to, is rate-induced autoregulation, also known as something called the Treppe phenomenon, okay? Or Treppe or staircase phenomenon. So you can see we have almost like a staircase going up here. All right, tensions along the y-axis, and we got time and our stimulus rate over here, time along the x over here. Okay, so this means, what this definition is, with an increase in heart rate, you will also have an increase in contractile force. Why is that the case? Okay, well, we're going to explain it. We know calcium enters in phase 2 of the transmembrane action potential that we've gone over. The duration of time spent in phase 2 is also rate dependent. So anything that increases rate time will be borrowed from that plateau phase of the transmembrane action potential. So then how can we have an increase in force if in fact there is less time in phase 2 for calcium to enter? That doesn't really make sense, right? So if we are actually decreasing the amount of time in that phase 2 where calcium enters, how do we have an increase in contractile force? How do we have an increase in calcium if we're decreasing the time calcium can come in? So actually, because calcium into the cell not only depends on duration of phase 2, but how many of them occur per minute. So even though each phase 2 has decreased amount of time individually, we have more of them per minute. So there will be less calcium entering in each individual phase 2, but there are more phase 2s per minute, if that makes sense, which ultimately is giving us an increase in intracellular calcium, which gives us an increase in contractility. So we can see this, right? So even though cycle rate is increasing and the time spent in phase 2 is decreasing, we have more cycles per minute. So therefore, we're actually going to enhance the amount of calcium in per minute. So then we're going to enhance contractility as well. Okay, so the last one is post-extrasystolic potentiation. This means or states that the beat following the premature beat will be much stronger than a premature beat. So again, this is all related to calcium. So the more time we have in between beats, the more calcium can enter into the cell, which will then increase the force of that beat following that premature beat, because again, it's related to time and all of that. So that beat following the premature beat will be much stronger. Again, related to calcium and time that calcium can enter into the cell, because we're having more time in between beats if we have a premature beat. So that gives us more time for calcium to enter the cell, which we can then increase the force of that beat following that premature beat. Okay, so finishing up this section of the lecture, we're going to talk a little bit about extrinsic mechanisms on influence onto the heart. So we just talked about the intrinsic mechanisms of the heart where it can regulate itself without neural or hormonal influences. Now we're going to talk about those neural and hormonal influences quickly. Okay. So we have two extrinsic mechanisms, neural and hormonal, okay? Okay, so autonomically, we have our sympathetic and parasympathetic nervous system again. Sympathetically enhances atrial and ventricular contractility, right? We're again talking about norepinephrine enhances this contractility because it binds to receptors which will cause the contractile response. Epinephrine also helps too, but again, remember as a neurotransmitter, norepinephrine is our dominant sympathetic nervous system transmitter. It's about 80-20. Epinephrine is our dominant catecholamine, and norepinephrine is less dominant hormonally, right? So it switches 80-20 there. So our concentration of norepinephrine in various locations within the myocardium reflects the density of the sympathetic innervation to those locations. So the more neural density you have, the higher concentration of norepinephrine there will be to those specific locations. The norepinephrine concentration is 3 times greater in the atria than in the ventricles. Why is that? Because due to the sympathetic density at the SA node and the AV node is so great, and then remember, it terminates also on the walls of the atria. So sympathetic stimulation to the myocardium is asymmetrical. So this means that the nerves that act on the left side of the heart have more powerful effect than on the right side of the heart as well. Okay, so now we just finished up with some of those mechanisms and heading into our last screencast for this lecture, we're going to then next talk about exercise and myocardial function.